this is where we ended up. A, B, C, D. Give me the products of the symmetrical and unsymmetrical epoxides under acid condition and under base condition. Whew. Okay, so let's try, see how well we did. I know that you're going to give me the correct answers. I know that you've already done it. Okay, well, maybe not, but I'll pretend like you are a good class. A good class. All right, so here's our A. For A, this is an unsymmetrical epoxide, and this is happening in acid conditions. So we need to predict the product, the major product that goes on. All right, so I'm going to redraw my reagent. There it is. I'll always do this, right? I think it sets it up. And this is an acid. Okay, so what that means is that that's an H plus, and that gets added on first. So that H plus is positive. It adds on to that oxygen. Oxygen now has to make a decision. Which side do I free up? If I look to the left, this is a primary carbon, and if I look to the right-hand side, this is a tertiary carbon. So this oxygen is going to say, okay, listen, I'm going to have to make sure the cray-cray one's taken care of first. That's always the kind of thing with epoxides. Make sure the crazy one has everything that it's need. So because of that, this oxygen says, tertiary, if I cleave you, you're going to be okay. I know that you'll be able to kind of figure out what to do with your life. I'm going to have to go over to the primary, and I'm going to have to make sure that this primary is taken care of. So that's the side that it decides to break. Now, the carbon is going to wait on another piece to come in. What is that other piece? What comes into the picture? Okay, well, normally a Cl would go here. And if I look at that Cl, the problem here is that this is also done in alcohol. And we saw this back in the day. Alcohol is an OCH3 group. That OCH3 group is a better nucleophile. So chlorine does go on in the first step, folks. It does go on. It goes on at that position. The problem, though, is that this CH3O group is a better nucleophile. It's prettier. So a substitution reaction happens. So this chlorine is going to get substituted with an OCH3. So that is the product for this reaction. If you messed this up, that's probably where it happened. You might have put the chlorine on it and called it a day. However, the problem here is that there was alcohol that was also involved. And that alcohol is a nucleophile, and that nucleophile can come in, and that nucleophile can react, and it can substitute that chlorine out. And that's what happens in part A. Okay, now let's take a look at part B. Part B was the same epoxide, but this time CH3O minus and CH3OH. Okay, so start off with your reagent. There you go. And this time it's a base. So the base is going to come in first. That's negative. And that base is going to look at these two carbons, and it's going to say, okay, oxygen, I'm here to help you out. We want to make sure the cray-cray one's taken care of first. So over to the left, you've got a primary. Over to the right, you've got a tertiary. So because of this, I'm going to take care of the cray one. You go over to the more stable one. So the OCH3 gets added on first. When that happens, this bond breaks, and that opens up for oxygen to become a negative charge. When that oxygen becomes a negative charge, we have to give it a proton somewhere. Where does that proton come from? Folks, the proton comes from the alcohol that's right there. So this is the H. That's the H source that turns that into an alcohol group. So a little bit different here, right? In the first round, acid attacked first. The O protonated first. The O took care of the crazy one. And then in the second round, the nucleophile came in. Nothing with the oxygen at all. The nucleophile came in and said, I take care of the crazy one. That way you can go off and be with the love of your life. And that's how oxygen breaks open the ring. Okay, let's look at C. C, we have an epoxide, and on this side and on this side, we have two methyl groups. So this is a symmetrical one, which is good. Here's HCl, and then we're going to bring in CH3OH. Again, just to reconfirm that. Oh, all right. So I'm going to start off with my reagent. There we go. So this is acid. Acid means this gets protonated first, and then the oxygen looks at these two carbons, and it says, hey, wait a minute. I don't really have a cray-cray one here. That carbon is tertiary. This carbon's tertiary. So it really doesn't matter which one I break up with. Either one's going to be fine. So I'm just going to choose the one on the right-hand side. It's symmetrical. We can do that. That's pretty easy. Well, when that happens, this carbon has an extra bond that it's got to come from somewhere. And that extra bond is first going to come with chlorine. So if we did not use this methanol here, I want you to understand that that chlorine would go right there. But we followed this up with methanol, and a substitution reaction is going to happen. That's why they've wrote it there. So this chlorine's going to disappear, and what goes on in its place is a OCH3 group. So OH on one side and OCH3 on the other. All right, now let's take a look at part D, which is the last example that they wanted us to do. And in this round, they want us to add OCH3, and then they wanted us to add CH3OH. Okay, so I start off with what they give me. Looks like this. So the OCH3 comes in first, and it looks at these two carbons, and it says, wait a minute, oxygen, you were kind of in a good thing here because neither one of these are kind of cray-cray. And that oxygen says, I know, but I can't really keep this up. So you're going to have to take one of them. So it really doesn't matter which one. I'm just going to put it here. So OCH3 is going to go there. So what that does is that this oxygen breaks that bond. That oxygen now forms a fully negative. So we need a proton source, and that's the purpose of the alcohol here. So that's going to donate the hydrogen to make that an OH group. And look at these two products. They are the same products. So here with the symmetrical alkane, or epoxide, sorry, a symmetrical epoxide, the acid condition based on those reagents and the base condition based on those reagents give us an identical product. The same. Again, very, very easy compared to the unsymmetrical ones where we have to question a little bit more. Okay. I'm going to take this another step further. I know, you're thinking, oh God, when's it going to stop? Just kind of hear me out for a minute. I'm going to go back into Orgo 1 and pull out a reaction. I want you to connect some pieces together. Let's take CH3, CH, CH3, CH, double bond CH2. And let's react this with H2SO4. And water. I guess I should put water here. Water and acid. Do you remember what happened? Do you remember what happened with this alkene reaction? Just bear in mind, I know it's not an epoxide. It's not an epoxide right now. But that's okay. Just kind of hear me out for a few minutes. If you remember correctly, I'm going to redraw my reagent. And in this type of reaction, we said that if we take an alkene and we react it with water and acid, The double bond breaks. There we go. Two sites of attachment open up here and here. And H and OH go on to the molecule. H comes in, and that hydrogen plays with other hydrogens. So hydrogen would go here at that moment, and that forms a CH3. Remember, hydrogens are real picky. You know, they're kind of snooty. Ew, I only want to play with people like me. That's what the hydrogen does. We call that a Markovnikov reaction. So this frees up a carbocation, right? However, this carbocation can look next door, and it can say, hey, listen, normally this OH group would go right here, but next door to me is a much more stable carbocation. It is a tertiary spot. So we see a carbocation shift that happens because a tertiary carbocation is a little bit better than a secondary. So it has to switch places, and it switches places with the hydrogen. We call that a 1,2 hydride shift. So for those of you who are maybe a little bit rusty in Organic 1, here we have an alkene. That alkene reacts with water and acid, and that forms an addition product. The water and the acid go on in a Markovnikov addition. So the double bond breaks, two sides of attachment open up, hydrogen gets added on first, that forms a full carbocation. That carbocation undergoes a 1,2 hydride shift, and that 1,2 hydride shift places the carbocation at the tertiary position. Whew! What a mouthful. But that's what you learned in Organic 1. If you followed that description, good job. You did your job very well in the very first semester. But a carbocation shift goes on, and then what we see is the OH group, finally from the water, goes in, and that is where the OH group goes. Look at this. This formed an alcohol. We now know that we can take this alcohol, and we now know that we can undergo different reactions with that alcohol in order to make different products. Okay, so that alkene reaction back in the day can be used to make an alcohol with, and now we can take the alcohol and use any of the reactions that we've talked about in the alcohol world in the first probably, it seems like 30 videos of this lecture content, and we can undergo any of those reactions to change this alcohol into something else. Well, there's actually another reagent that I can now talk about. This was one version, and that was only one version. There's another way we can make an alcohol from an alkene. Let's take the same starting product, or reagent, sorry. And instead of water and acid, let's use something called MCPBA. Oh, gosh. Look at that abbreviation. That's got to stand for something horrendous. What does MCPBA mean? Okay, well, MCPBA, the M stands for meta. You don't know what that means yet. That's okay. We'll get there. The C stands for chloro. The P stands for peroxy. And the B stands for benzoic. And the A stands for acid. This is a reagent, a meta chloroperoxy benzoic acid. We've seen peroxies before, haven't we? Of course we have. I told you a video or two back, hey, one of the ways that we can make an epoxide is if we add on a peroxy acid to a double bond. This just so happens to be one of the most common peroxy acids that we use, MCPBA. That is what that is. That is a peroxy benzoic acid, but it's still a peroxy acid. This structure looks like this. It is a ring structure with a ring, a proper benzene ring, We have a chloro on it, as you can imagine. The meta is an insight of the location of where these groups are going to be. And here I've got a C double bond O, and a peroxy acid would typically be OOH. And that's what we see here as well. There is my meta chloroperoxybenzoic acid. So this is a way that I can take an alkene, react it with a peroxy acid, and do what? We make an epoxide. Okay, so CH3, CH. So this is nothing new. This is just a review as well, because we saw these reactions in the alkene world. So the double bond breaks. There we go. Peroxy acid is added, and here is the peroxy acid. That makes an epoxide. You see where I'm going with this now? And that epoxide, we know, can undergo reactions. We just talked about them. They're acid and base reactions. So that epoxide ring will open up. And it really depends on what I do with it at this point. But here's the kicker. I've just made an epoxide. That's good. I can react this with acid, break the ring just like before. I can react it with a base and break the ring just like before. But what I can also do here is add something LAH. Now this is new for everybody. LAH is going to stand for lithium aluminum hydride. And lithium aluminum hydride is going to be a hydrogen donor. And if I look at this molecule, this epoxide, and I add on LAH, I'm just going to redraw what we have from up above before I do anything else. So that's what we have. The LAH is going to open the ring up. As you can imagine, it opens the ring up. The LAH is a hydrogen donor, and that epoxide ring will break. Well, this is hydrogen donor, but it's a hydrogen minus. What does that minus mean? It's not an acid. This is a weird little base. That's what the term hydride means. Inorganic sometimes. A hydride is a H-, and that H- is going to act as a base. So let's think about what happens with bases here. The base is going to come in, and it's going to go, hey, oxygen, I'm here to save the day. Which one do you want me to take? I'm going to take the cray-cray one, so that way you can go on. And this carbon to the left is going to be a secondary. This carbon to the right is going to be a primary. So that hydrogen, which is negative, that's the weird thing about this, is acting as a base, and that hydrogen's going to go, okay, I'm going to go here and take care of the primary, so I'll change that to a CH3 group, and that will allow you to break this bond, and then you can go over to that secondary carbon. So here we have an O-. Well, that O- is going to reroute yet again. We need a proton to go on this thing, and we can give it that later on down the road, just like before. Now, why did I go through this route? Because compare the top version to the bottom version. I know it seems like a lot. I know it does. Route number 1, this was a traditional organic 1 reaction that broke a double bond, added water to a double bond. We saw a shift, and that shift made it go to the tertiary spot. What if I didn't want it to go here? What if I did not want that OH to go there and I wanted it to stay put? how could I prevent the rearrangement from taking place? Well, you might say, well, we use something like an anti-Makovnikov reaction. Well, that's a good try. But an anti-Makovnikov would have put the OH group here on the end. And I don't want it there either. So a normal traditional alkene reaction would break the double bond and end up putting the OH group here. Maybe I don't want it there. A anti-Makovnikov, you know, the borane, THF, peroxide, water, all of that was kind of introduced in the alkene reactions as well. That would put it on the end. I do not want the OH group on the end either. I want the OH group right here. How can we do that? No option that we've talked about so far will allow me to do it except for now making an epoxide. So I take that double bond, I add a peroxy acid. In the past, we've just said peroxy acid. That's really all that we've said. We're just going to add peroxy acid and we make an epoxide, and that's where we stopped. Well, here we are defining one of the most common peroxy acids now, MCPBA, metachloroperoxybenzoic acid. That forms the epoxide, but we're going to take it another step because now we know the reactions of an epoxide. So if we take it another step, at this point, if I want that OH to go in that location that I've identified up here in the very top, if I want it to go right there, I have to make sure that no rearrangement is going to take place. So epoxide will allow that to happen. I add a base onto this. I don't want to add on a base, though, that's going to add on another group. I mean, if I add on OCH3, that's going to add that piece onto that molecule. Maybe I don't want that. If I add in an O with anything else, that's going to add on to that molecule. Maybe I don't want it. Maybe I just want a simple hydrogen. If that's what I want, LAH is the reagent that you want to use. Lithium aluminum hydride. It gives the molecule just a simple little low hydrogen. That hydrogen acts as a nucleophile, which is very good for us sometimes. So this allows us to add on the hydrogen and not really mess with the rest of the molecule. So hydrogen gets added on to the end in a normal, typical base epoxide reaction that frees up the oxygen, and now eventually we'll give that oxygen a hydrogen, so that way it becomes an OH. And this lets me have an OH onto this carbon that the other two routes would not let me have. As far as lithium aluminum hydride, folks, this is what it looks like. So here's your LAH. Again, it is a hydrogen donor. The structure of this is a salt. You can kind of almost tell this grayish substance over here in this bottle to the left or to the right. Lithium, of course, lithium is going to be there, Li+. And then the anion piece is the aluminum containing piece. And that aluminum containing piece has 4 hydrogens, and one of those hydrogens will be donated. And that is where that hydrogen is coming from. All right, so there's going to be more about lithium aluminum hydride much later. We're going to talk about a section of organic called organometallics. And this is the area that this really falls into a little bit more. So this is kind of get your feet wet with LAH, and we'll see more of LAH a little bit later in a different lecture module. But here's your introduction to that reagent. Brand new for everybody, never seen it before. All right, so now let's take a look at an example problem. Let's just kind of wrap this stuff up together. I know it seems like a little bit of tangent that happened here, but I want to prove to you that it wasn't necessarily a tangent. You're getting it. I know you're getting it. Just bear with me. So problem, how can the following compounds be prepared from 3,3-dimethyl-1-butene? So this is where I'm going to stop the video. In the next video, you know how this works. I'm going to go over A and B, double check your answers with mine, and see where you messed up, if you messed up. So what they want is 3,3-dimethyl-1-butene. I'm going to give you that structure just so you have a starting place. It's another quick review of what nomenclature of alkenes are. So butene is 1, 2, 3, and 4. On 1, we have the ene, which is the double bond. And then on 3, we have a methyl group, and on 3, we have another methyl group. So this is the structure that they want you to start with, and they want to know, how do you make A and how do you make B? What reagents are going to be required in order for you to get to that point? All right, so try a stab at it, see what you come up with, use what we just talked about, the traditional alkene reactions back in Orgo 1, and then now this new epoxide reaction that we took another step forward so that we could break that ring open and maybe prevent rearrangement from taking place. See what you come up with. In the next video, we'll answer it together.